Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on August 11, 2025, just 4 days ago. The big hook is a new class of action reasoning models that split robot intelligence into 3 stages, turning camera input and instructions into depth tokens, and editable on image trajectory trace, and then precise actions, delivering explainable, steerable control with strong gains like 70.5% zero-shot success on simpler ENV. The paper is titled MolmoAct, Action Reasoning Models That Can Reason in Space. And as we will see later, the implications for real robot control are significant. Beyond benchmarks, the team releases an open dataset and model weights that boost generalization and cut training cost. Building on that, the tweets echo the 3-stage pitch. Depth to trace to actions, highlighting manipulation and visual reasoning, the open dataset, and lighter pre-training compute. Engagement looks solid, with likes around 195, 137, and smaller threads discussing details. Alright, this overview graphic shows the full pipeline at a glance. Data sources on the left feed a 3-stage model in the center, which takes an instruction and image as input, then reasons in space to produce depth tokens, a visual trace, and finally, robot actions. Moving right, the panels highlight deployment in varied real kitchens and a steerability demo, where a user-drawn yellow path adjusts the trajectory. Building on our intro, the takeaway is transparent planning that you can see and edit. Next, this split diagram clarifies the training and usage flow. On the left, pre-training feeds a vision language model with mixed robot and web data, teaching depth prediction, trajectory drawing, and discretized control. On the right, the trained action reasoning model takes multi-view images and either a natural instruction or a user-drawn trajectory, then outputs 3 streams: depth tokens, a visual trace, and final action tokens. The key message is modular learning first, then editable spatial reasoning at inference. Okay, this figure compares the overall pre-training mixture to the actually sampled subset. The left pie shows the raw pool, roughly equal shares of action reasoning and trajectory condition data, a sizable multimodal web slice, and tiny depth and line traces. The right pie shows the sampling rates used during training, where depth and line are boosted to 7.5% each, multimodal web is trimmed to 5%, and action reasoning and trajectory condition data each rise to 40%. The legend clarifies the colors. Now, this table benchmarks a wide range of policies on simpler ENV with 2 suites, visual matching and variant aggregation, each broken into pick co-can, move near, and open or close drawer, plus an average. Focus on the shaded rows near the bottom. The zero-shot model reaches 70.5% average on visual matching, edging out strong baselines, and the fine-tuned version climbs to 71.6%. On variant aggregation, fine-tuned performance lands at 72.1% average, indicating solid robustness across task variants. Moving to the results, this table reports Libro success rates across 4 categories with an average column. Focus on the bottom row, which shows the 7 billion depth model scoring 87.0 in spatial, 95.4 in object, 87.6 in goal, and 77.2 in long horizon, averaging 86.6%. Building on earlier gains, the strongest baseline trails by about 2 points on average, and the gap is largest on the hardest long horizon tasks. Building on those results, 2 takeaways stand out. First, explicit spatial reasoning, from depth tokens to a drawable visual trace to discretized action tokens, delivers clearer planning and stronger generalization. Second, the open mid-training dataset and efficient pre-training make this practical to adopt. Thanks for tuning in. That is the AI Research Roundup. I'm Alex. Thanks for listening.